For my final environmental fate and transport project, I decided to model the bioaccumulation of methylmercury in the different trophic levels in a contaminated lake. First, I will go over the background of methylmercury, which includes the health impacts, methylmercury formation, and an overview of bioaccumulation. Second, I will talk about the objectives of my study. Then I will go over the methodology of the study, which includes the overall approach, equations, observational data, and assumptions. I will then go over my MATLAB code, followed by the results and validation. Finally, I will talk about the different environmental, economic, and societal impacts, as well as any further research that is needed to be done. Mercury is the third most toxic substance in the Agency for Toxic Substances and Disease Registry. Methylmercury is the most toxic form of mercury and has many negative effects to human health if consumed in great doses. The reference dose, or RFD, for methylmercury, according to the EPA, is currently 0.1 micrograms per kilogram per day. If consumed in doses greater than the RFD, then there is a significant chance for developing neurological issues, especially in developing organisms such as pregnant women and children. Methylmercury is especially dangerous to fetuses due to its ability to cross into the placenta and enter the fetus's blood and brain, which leads to neurological issues. Methylmercury is formed from elemental mercury that is emitted from both natural sources such as volcanoes and geothermal springs and anthropogenic sources such as coal combustion, waste incineration, industrial uses, and mining. When emitted, mercury can travel long distances in the atmosphere before being deposited into water bodies. Therefore, it is often difficult to pinpoint the direct source of mercury emissions that are responsible for the pollution of lakes. Mercury is usually highly present in the sediments of near-shore environments, and sediment resuspensions are often the main source of mercury in a water column. Once deposited in a water body, the mercuric ion is not absorbed by aquatic creatures and adheres to sediments on the lake floor. Methylation of mercury takes place when anaerobic bacteria transform Hg2 into the methylmercury ion. Methylmercury is considered a toxic heavy metal that is non-biodegradable, meaning that it won't naturally break down into its non-toxic forms. Methylmercury is very soluble and can be readily absorbed in fish, giving it the ability to bioaccumulate in the ecosystem. Methylmercury also biomagnifies as you move up the food chain. For example, percentages of methylmercury out of the total amount of mercury ranges from 10% in phytoplankton to 95% in top predator fish. Bioaccumulation is the increase of mercury levels in fish with age, while biomagnification is the increase of mercury levels through the trophic levels of the food chain. The driving factor of how much methylmercury is bioaccumulated is the difference between uptake from respiration or food and elimination from excretion or dilution. Therefore, it is important to understand the biological components of each species in the food chain of the aquatic system. Modeling the bioaccumulation in an ecosystem can be done through the use of toxicokinetic models that explore how the concentration of a toxic substance is accumulated over time based on the species-specific uptake and excretion rates. The objective for this study is to model the concentrations related to the kinetic bioaccumulation of methylmercury in trout over a designated time frame. The overall goal is to obtain methylmercury concentrations for the water body and each trophic level in order to show the buildup of methylmercury in the food chain. This will help determine the time frame of when fish contaminated with methylmercury passes the acceptable threshold of what is healthy for humans to consume. This study will be done through the use of a biokinetic model that expresses the change in concentration in the designated species over time. In addition, another kinetic model will be built to explore the change in methylmercury concentration in the water due to methylation and demethylation of Hg2. My overall modeling approach was to first find the core kinetic equations and key rate constants through thorough research of other published studies. I wanted to find one equation to model the chemical methylation rates and another equation that represents the bioaccumulations throughout the different trophic levels. The next step was to formulate these equations into ones that can be input into MATLAB through integration. The MATLAB code was set up by inputting these equations into a for loop that changes concentration with each time step. The final concentrations for each trophic level and the water body were then plotted over a time period, and the final results were observed and discussed. The mathematical models at the core of this study include two mass transfer models. The first core equation, equation 1, explores the change in methylmercury concentration over time. This equation was obtained from a journal article, Olson et al. 2018, that explores the chemical kinetics and transformations of mercury and methylmercury in a water body. The integrated form of equation 1 that will be introduced in a MATLAB code moving forward is shown in equation 2. The second core equation, equation 3, explores the change in wet weight methylmercury concentration in the fish over time. The inputs of this equation are from respiratory and diet uptake of methylmercury. The outputs of this equation are from respiratory output, excretion, biotransformation, and growth. A visual representation of this specific mass transfer model can be seen in Figure 1. The integrated form of equation 3 that will be introduced in a MATLAB code moving forward is shown in equation 4. Equation 4 makes a simplification by introducing a variable kt, which is defined in equation 5 as the sum of all the output rate constants. Equation 6 defines the variable kv, which is the respiratory output rate constant. The respiratory output of methylmercury greatly depends on the lipid content L of the species of interest and the octanol water partitioning coefficient KOW. Equations 3 through 6 were obtained from a journal article, McKay et al. 2018, that models the bioconcentration, bioaccumulation, biomagnification, and trophic magnification of methylmercury within a food chain consisting of phytoplankton at trophic level 1, zooplankton at trophic level 2, mysis at trophic level 3, smelt at trophic level 4, and trout at trophic level 5. The model in this study is a simplification of the one performed by McKay due to generous amounts of information, such as rate constants for specific organisms that was unable to be found from other sources. The key parameters that will be used in this study can be seen in this table. That includes the rate constant values and abbreviations that are used in equations 3 through 6 for the specific organisms that will be studied. These values include the lipid content, respiratory uptake rate constant, diet uptake rate constant, growth rate constant, excretion rate constant, biotransformation rate constant, and respiratory output rate constant. Because all of these values are dependent on the species of interest, each species studied in this model has a different value. The species that I chose to study are zooplankton, mysis, smelt, and trout. The key parameters relating to methylmercury can be seen in this table. This includes the octanol water partition coefficient, methylation and demethylation rate constants, the bioconcentration factor, and the molecular weight of methylmercury. The wet weight fish concentration, water concentration, and diet concentration are all values that will be solved for in my MATLAB model. In order to perform this model, some assumptions had to be made. It was assumed that there would be a one-time deposition of mercury into the lake. It was also assumed that demethylation of methylmercury is not occurring, meaning that methylmercury is only being created and not destroyed. Also, I had to assume that the fish will continue to live throughout the time frame of the study. When performing the first trial run of this model, I came across some issues while using the KOW and KV values, so I omitted these from the model. It was found that these values didn't contribute to an extreme amount of methylmercury losses in the fish, so it was a safe assumption. It was also assumed that each trophic level is only receiving methylmercury from respiration and from eating the trophic level immediately before it. This is obviously not how the real world works, but modeling a complete food chain would be extremely difficult to do. Finally, I assumed that zooplankton are only receiving methylmercury through respiration, as I could not find enough information to model what they eat. The The first step in making my MATLAB code was to input the methylmercury chemical rate constants such as the methylation and demethylation rate constants. The amount of mercury being deposited was also inputted in this step. Through research, I found that the average mercury concentration in a water body is 1.92 nanograms per liter, which equates to 1.92 times 10 to the negative 6 parts per million. The next step was to input all bioaccumulation rate constants that were discussed previously. This was done by using vectors to represent the different organisms, with zooplankton being the first value, followed by mysis, smelt, and trout. A for loop was used to loop through the different time steps of this code. I chose a time step of 0.1 days, which creates a time vector from 0 to 35 days. The for loop includes the integrated equations that were discussed previously. The water concentration is calculated first, followed by the concentration in zooplankton, mysis, smelt, and trout. Each equation contains the current water concentration for that time step, and each trophic level contains the current concentration of the trophic level immediately preceding it. This for loop creates 5 vectors containing the concentration of water and all trophic levels changing with time. The final step of the MATLAB code is plotting the results. 2 figures were created, one with the concentrations of plankton, mysis, smelt, and trout versus time, and the other contains the water concentration versus time. These are the final graphs that were created on MATLAB. The graph on the left is the methylmercury concentrations throughout the different trophic levels. These results are interesting, but also expected, as the concentrations in zooplankton seem to reach steady state, but the concentrations in trout and smelt never do. Since the zooplankton are only receiving their methylmercury from the water, when the water reaches steady state, so do the zooplankton. Once the concentrations of the lower trophic levels have started to increase, the trout concentrations soar, which is due to the biomagnification potential of methylmercury. This graph truly shows that bioaccumulation is occurring because you can see that concentrations are increasing as the trout's age increases, and also biomagnification is occurring as concentrations are increasing as you move up each trophic level. The graph on the right shows the methylmercury concentration in the water. This graph shows that without demethylation occurring, methylmercury reaches steady state after about 25 days. The final data can be compared to previous studies to ensure that the results are within an acceptable range. The average mercury levels in Great Lakes fish range from 0.05 to 0.55 parts per million, and my final results after 50 days range from 0.045 to 0.36 parts per million. This indicates that my final results are within a typical range and my model was successful in modeling methylmercury concentrations in fish. I also compared the value I found for methylmercury steady-state concentration to previously published data. The data shows that the arithmetic mean concentration of methylmercury in an Ontario water body is 0.105 nanograms per liter, which equates to 1.05 times 10 to the negative 7 parts per million. My steady-state concentration for methylmercury was about 1.55 times 10 to the negative 7 parts per million, which is around the research value. This shows that my model was successful in modeling the concentration of methylmercury in the water. According to my results, methylmercury starts to build up to a dangerous level in the ecosystem after about 45 days. High levels of methylmercury have negative environmental impacts, such as potentially killing any animal that eats it and causing reproductive problems that can lead to endangered species. The most at-risk species are humans, otters, eagles, loons, bears, and more. High methylmercury concentrations can also negatively impact the economy, as the fishing industry will see loss of production and profits. Public health is also at risk. According to my results, trout is considered above the EPA's human health criterion after 45 days in the contaminated water. Ideally, I wanted to conduct my study on the effects of bioaccumulation of methylmercury on the human body. However, more research is needed for this to be done. The human body is a complex system with an extensive amount of possible sources and sinks. Researching this area would require extensive human, metabolic, and biological knowledge.